Hey, welcome back. Today, we're going to play a little guessing game. But trust me, this is no ordinary game. Hidden inside is one of the most powerful and honestly elegant ideas in all of computer science. So let's just kick things off with a challenge. I'm thinking of a number somewhere between 1 and 1 billion. Seriously, how many guesses do you think you'd need to pinpoint it? 1 million? 500,000? It sounds kind of impossible, right? Okay, the rules couldn't be simpler. You just guess a number. And all I'm going to tell you is whether my secret number is higher than your guess or if it's lower. That is literally the only information you get. Now, if we were to code this, the feedback would come from a handy little function. Let's call it the guess API. If your guess is too high, it gives you a -1. Too low, it gives you a 1. And if you somehow manage to get it right, it returns a 0. That's our compass. All right, so with that set up, let's actually tackle this thing. What's the first strategy that pops in your head? Well, the most obvious way to do it is just start at the beginning, right? Guess 1. Nope. Okay, how about 2? Then 3? This is what we call a linear search, or kind of the brute force approach. You just plow through every single possibility one after another. And the problem with that? Well, if my secret number happens to be, 999 million, you're going to be guessing for a very, very long time. In the worst case, you'd need 1 billion guesses. There has to be a better way. So, let's forget about working harder. Let's work smarter. How can we squeeze the absolute most information out of every single guess we make? This right here, this is the light bulb moment. What if, instead of just knocking out one number at a time, every single guess we made could wipe out half of all the remaining options? That would completely change the game. So let's see how this halving idea actually works in practice. We're going to use a much smaller example, just to make this super clear. Let's forget about 1 billion for a second. Imagine the secret number is just somewhere between 1 and 10, much more manageable. So instead of starting at 1, the smart play is to go right for the middle. Between 1 and 10, the middle is 5. So our first guess is going to be 5. Now we ask our little API for feedback. Let's say we call guess 5, and it spits back a 1. What does that tell us? It tells us our guess was too low. The real number is higher than 5. And boom, this is where the magic happens. Think about it. Because we know the number is higher than 5, we can completely throw away the numbers 1, 2, 3, 4, and 5. We just cut our problem in half with a single guess. Our new search range is just from 6 to 10. So this just becomes a simple rinse and repeat process. You find the middle of whatever range you're looking at, you make a guess, you get your feedback, and you chop away the half you don't need. And you just keep doing that until you've cornered the answer. This logic is so clean, so efficient, it's just begging to be turned into code. So let's see what that looks like. Okay, here's the game plan in plain English. We're going to set up 2 markers, or pointers. A left one at the very beginning of our range, and a right one at the very end. We keep guessing the middle, and based on the feedback, we either slide the right marker down, or we slide the left marker up, shrinking our window until they meet. And what's so cool is that the actual code mirrors that logic perfectly. Look, you can see our left and right variables getting set up, you see the while loop that keeps the process going, and then that simple if-else statement is just deciding whether to move left or right. It's a perfect translation of our idea. So just to be super clear, left is the floor of our search area, right is the ceiling, and mid is just our guess for that round, smack dab in the middle of our floor and ceiling. Okay, so this works great for small numbers. Let's bring it all the way back to that original crazy problem. Why is this method so ridiculously fast for gigantic numbers? Well, the difference is it's night and day. A linear search just kind of plods along, one step at a time. The time it takes grows directly with how big the range is. In computer science, we call that O(n) time. But binary search, it's different. It slices the problem in half, over and over. This is called logarithmic time, or O log n. And it is insanely faster. Just look at this table. This really says it all. For 100 numbers, it's 100 guesses versus 7. For 1 million, it's 1 million guesses versus just 20. And the bigger the range gets, the more jaw-dropping the advantage for binary search becomes. And that brings us to the grand finale, the answer to our very first question. How many guesses to find a number between 1 and 1 billion? The answer is about 30. That's it. 30 guesses to find one specific number out of a billion choices. So really, the big takeaway here is that the right algorithm can take a problem that seems completely impossible and just make it trivial. It turns this monumental task into something your computer can do in the blink of an eye. And that's the power of thinking this way. It just makes you wonder, what other huge, messy problems out there could be solved if we just figured out the cleverest way